All right, good afternoon. Let's start the lecture. All right, so let's continue on the Z transform. In the previous lecture, we learned about basically the definition of a Z transform, which I illustrated it here. Basically, you are working on, if you look at the result, the formula right here, you're using a sequence of numbers and then to form a power series, and that basically gives you the Z transform, right? In terms of notation-wise, okay, if you have a original, let's say, time function x of t, and we can obtain a sequence number from this x of t by appropriate sampling, right? And you can use capital X of z representing the Z transform. So if you have seen basically either one of this, right? So they're all referring to the same thing. You're doing Z transform for Z to the sequence number x of k here. Okay, yeah. And we learned basically what's the Z transform for typical functions like a step function, delta function, Kronecker delta, sinusoidal, right, and exponential. So now today we're going to look at is we'll look at the inverse Z transform. Okay. So inverse Z transform essentially means you are given x of z, and then to derive for x of k. So that's the inverse Z transform. I'll present you a number of different ways of performing this inverse Z transform. Okay, some very common ones. Okay, so first of all, let's look at the first method here. Okay, yeah. The first method we're going to look at the so-called power series, okay, method. So power series method, if you look at basically if you look at the definition, right? So from the definition, what we have is your x of z equal to x naught plus x1 and plus x2, and then keep going. So that's your, if you expand this power series, this is your definition, right? This is basically what x of z is. So, but what's given may not be in this. So let's, for example, you're given x of z, which is z over z squared minus 3z plus 2. So, for example, you're given this expression for x of z. So this is definitely different from the definition, right? This looks different. Okay, it's more of a compact form, converged form for x of z. Okay. So the idea is, if you look at the definition, we're looking for x of k. So we're basically looking for what? We're basically looking for what's this. That's your x of k, right? You know, x of k at each instant. And somehow, if we can extract those x0, x1, x2 based on the given expression for x of z, then we got our x of k, right? So that's the idea. Okay. And the power series expansion at here, power series method here, essentially it's what they're doing at here. So what it does is, this is very much like what you learned in high school. You're going to do a so-called long division, right, to obtain this x of k. So we're going to do a basically, let's do a long division at here. Okay. So z divided by z squared minus 3z plus 2. Okay. So let's see, how do we do the long division? So we'll start to do the long division. essentially you like a divided by b, and you're looking for what's the quotient, what's the remainder, right? That's long division. So in this case here, let's say this divided this. If you want to put something the same order here, then you need to multiply by z to the power -1, right? Multiply z to the power -1 with this expression, then you're going to get z minus 3 plus 2 times z to the power -1, right? And then you can use this minus that, so we're going to get 3 minus 2z to the power -1. Okay, so let's keep going. Just do a few more steps out of here. Let's do one more step maybe. So now the next one, do the same thing. Something multiplied by the numerator, so you get the same order as this 3 minus this. So apparently it's going to be 3 times z to the power -2. Then you're going to get 3 at here, and you get 9 z to the power -1 here, plus 6 -2 here. Okay, so use this minus that, you get a 7. Okay, so that's how you basically carry on the rest of the calculation in here. So if you do the rest of the calculation a few more steps, you're gonna get okay, so on the quotient here, you're gonna get this. Okay, yeah. So it's not a division that you can finish in a few steps. Okay, it's actually probably infinite number of steps. But that's okay, because what we're really looking for here is looking for the coefficient in front of this z to the power -1, z to the power -2, right? So this chunk out of here, right? So this chunk, and plus all the infinite, the rest of the term, is what this equal to, right? So equal to this long division, or to the x of z. So apparently, if you compare coefficients, right? If you compare coefficients, okay, so I'm looking for x of k, which is the inverse z transform of the x of z. And now, I don't have, now unfortunately we don't have a beautiful one expression, but what we do have here is just a discrete sequence of numbers here, right? So apparently you look at this discrete sequence number for x naught, which is the coefficient for z to the power of 0. There's nothing. So x naught must be what? 0, right? So it must be 0 here. Okay. And then x1 is the coefficient to z to the power -1, so that got to be 1. And then here is 3, 7, 15. So keep going. So that's the x of k, right? That's your basically results based on this power series method. Okay. Now, if you're sharp enough, and then you look at this one, oh look, this is basically 2 to the power of k minus 1, right? For each one of this, when k equal to 0, 1, 2, like this. Okay, yeah. But often in time, you probably can't see from the sequence number here to this one single expression at here, right? So that's fine, yeah. But that's one method, right? So you get your sequence of numbers using this long division method, okay? But apparently you can see this is a fairly manual and cumbersome process to give you results for the x of k here, right? So what we do want is we want something like this in one shot. Somehow I'm able to get a results for x of k, end up with a this kind of expression in here, right? That's what we want. So this is basically the second method here, which is a very common method, which we would call that power fraction expansion method. Okay, power fraction expansion method. The gist of this power fraction expansion method is actually based on available information that I gave it you yesterday. This basically this Z transformation table right here. So, for example, let's see if we have x of z given in a format of course, a numerator divided by denominator. Okay? Yeah. Now, let's suppose that I'm able to decompose, okay, or this is basically a partial fraction expansion. If I'm able to decompose this this fraction into a number of fractions, addition of a number of fractions. Okay. So I'm not sure what divided by what, right? Let's say if I'm able to do this, okay, decompose this into a number, addition a number of fractions that are here. Okay, it's not going to be a random decomposition or a partial fraction expansion. It's going to be a purposely framed partial fraction expansion, so that each one of this, okay, basically we call that, we get the so-called simplest format, simplest form of fraction. Okay, simplest form. So you basically you can't do any more, or you don't need to do any simpler fraction anymore. By simplest form of fraction, what that means is basically means this is the fraction we're looking for. Okay, so we're looking for a fraction in this kind of format. Somehow we decompose it into this kind of fraction, this kind of fraction, or this or this. Okay, why? Because I have this one available already, right? And I can just look at the table saying, okay, what's the inverse of this? It's this, right? Or what's the inverse of this? It's this. Right? So that's the idea of so-called the simplest form of fraction in here, right? Basically, what I mean in here is the form or the format, okay, given in Z table. Okay, yeah, that's the idea to how we want to expand this partial fraction expansion. Okay, yeah. So I'm going to use a different scenario right here to talk about this partial fraction expansion. Okay, so let's look at the case number 1. Okay, this has a lot to do with the type of pose for the denominator d of z at here. Okay, so let's look at the first simple one. When poles are all distinct real. Okay, so when the poles, okay, poles basically means, if you recall that, poles means what? Poles means they are the roots of the denominator. Yeah. Okay. So that's how you look at this case. If you let the denominator to be 0, and you find, look, the poles are all real, distinct real, so different. So then you're falling into this case number 1 at here. All right. Yeah. So let's look at one example at here. Okay. Yeah. I'll use a little bit more. Well, let's consider general here. Okay. Yeah. So, for example, if I have capital X of Z, okay, and equal to a certain numerator, okay, and divided by, okay, the denominator, which is in this format, okay, and P1, P2, okay, are real. Distinct real or real numbers. Okay, that's what we call this case number 1 at here. Okay, case number 1. Okay, so partial fraction expansion at here, essentially what it does is, okay, you already, okay, actually at least when you learn Laplace transformations, the inverse Laplace transformation, you have the same basically idea for using partial fraction expansion to find the inverse Laplace, right? Now here we actually don't do the partial fraction expansion immediately on this one here, which means again, okay, I guess a minus this. You do this, right? This is what basically partial fraction. You got this, but don't write this yet, okay? But this is not what we do at here. You don't really do this right away. The reason, I'll explain the reason here. What you do is, okay, you will do a partial fraction. So you do this partial fraction on x of z over z. So we do the partial fraction not on x of z, but on x of z over z. Okay? So let me explain why. Okay? But let's say if I do this, basically what we were doing is we divide by both sides by a z, right? So divided both sides by a z like that. Okay? Yeah. So then very possibly you could have basically a partial fraction expansion now will be looking like this now. Okay. Now this n of z, a lot of time this n of z contains a factor z. Okay. So basically the n of z, okay, may be equal to z times something. Okay, so there is a z component there for the z, for the n of z. So when you divide it by z both sides, then your numerator basically just simplified a little bit, right? The z is gone. Okay, yeah. So you do your partial fraction expansion on the x of z over z. Okay. Now there's one scenario. Maybe your n of z is just 1, right? Could be. Right. So if you divide it by both sides by z, then you end up with the extra z on the denominator, right? Yeah. But then in that case, then you would actually just add a c over z, yeah, as a typical term here. Okay. So, but that's the point here. You do your partial fraction on x of z over z. Now, why do we do partial fraction on x of z over z? So think about this, right? You do the partial fraction over z, and you will be able to find a and b. Okay, and finding the a and b is quite easy. So the a at here is equal to z minus p1, okay, times the original x of z over z. Then you let the z equal to p1, and you'll find this value for the a at here. And same thing, you'll find the b by doing the similar operation, and you'll find the b value. Okay. So suppose you find the a and the b value at here. Okay. Now maybe 1 or 2 or whatever, right? You put it here. So now if you look at the z transformation table, okay, if you look at the z transformation table here, you look at all the simplest formats on the last column here. What is the commonality? If you look at the numerator, what's the commonality here? Can you see that? There is always what? A z term on the numerator, right? There's always a z term on the numerator. Now back to this partial fraction expansion. I find my a and a b, then I will multiply the z back to the right side, right? So I will get a times z over z minus p1 and b times z minus z p2. So now I have this, and this is exactly what is available inside the table here, right? Yeah. So I can immediately use the table to say, okay, so the inverse for this guy is that, and for this guy is the other, right? So that's save you tremendous amount of work by using the table because it's available now, right? So that's why we do a division of a z first, okay, and then put it back so we can make use of the table. Is that good? Right? Yeah. So basically, just remember, if you're required to do a partial fraction expansion to find the inverse z transform of a certain expression, we divide it by z first, and then we do the partial fraction expansion on the resulted expression. Right? So let me show you an example here. Let's say we have a x of z equal to z divided by z minus 1 over z minus 2. So as you can see, in this case, the numerator actually has a z factor in it, right? Has a z factor. So if I divide it by z for both sides, then the numerator will become 1. Okay, so let's just simplify a little bit here, right? Yeah. So maybe I'll show you another different example here. Let's say if my numerator here is this, right? Then for this particular one, so you actually will end up with this. Does that make sense? Right. Okay. So if I do partial fraction now, I do partial fraction expansion on, let's say I'll just do this on both sides here. Do this on this one here, we got a over z minus 1 and plus b over z minus 2. Okay. And this one, it would be what? Let's see, a over z minus 1, b over z minus 2, and then c over the z, right? Okay. So that's the only difference. Yeah. But in terms of finding ABC or AB at here, you use the same approach like this one. Okay, same approach to find A here. So let's try it. So to find the A, it's equal to z minus 1 times x of z over z, and which is z minus 1 times z minus 1 times z minus 2. Okay. And after that, you let z equal to 1. So this one and this one cancel first, and then plugging z equal to 1, which is 1 minus 1 over negative 1, which is negative 1, right? Negative 1. Okay. And similarly, you can find the b value, which is 1. Okay, you'll find the b value by using the same approach. You find 1. So you probably should try this. What does a equal to here? What does b equal to at here? And what does c equal to at here? Okay. Yeah. So once you find this one here, we simplify it and now say, okay, so x of z divided by z equal to negative 1 over z minus 1 plus positive 1 over z minus 2. Okay, that's your first one here. Then multiply the z back to the left side, right side. Okay, that's your x of z. Finally, you do an inverse z transform. So your x of k, which is the inverse z transform. And now you can use the table now, right? Use the table to find this and that. That gives it basically your little table. So here's the table right here. Okay. So this negative is just basically a 1 to the power of k, which is always 1. So negative 1. And here is z over this, so it's 2 to the power of k. And the k start from 0, 1, and 2, like that. Okay. Is that clear? Yeah. So that's a very simple one in terms of the partial fraction expansion, working on the scenario when poles are all distinct real. Okay. Yeah. If you're coming back to this one and here, okay, let's do this one. Let's say suppose you got a c equal to 1. So assume you got a c equal to 1. So you got to basically turn 1 over z at here, right? Yeah. And you'll multiply the z back to here, right? So when you multiply the z back to here, then this term on the right side is basically just 1, isn't it, right? So if you look at the table, which one is what does it mean? Yeah, so which one give you a 1? When n equal to 0, basically corresponding to the Kronecker delta, right? So you got, so basically here you're corresponding to delta k, right? So this term here, but it's just going to be 1, okay? Not 1 over z. Does that make sense? Yeah. So that's the idea, huh? Yeah.
So if you have 1 over z minus 1,
1 over z. Yeah, 1 over z minus. You mean?
It's going to be a delta function at 1.
Come again. What do you mean by?
So 1 over z minus 1. Yeah.
1 over z to the power negative 1. You mean?
No, minus 1.
Oh, minus 1. Yeah.
So is that going to be a delta function?
No. So if you're it's like this term now, right? So if for this term is z minus 1 here.
Right.
Yeah. So when you multiply the z, when you multiply the z back over here, right? So in this case, it cancel this z, right? You probably were thinking there might be a scenario. It's like this. So let's say you start with an expression like that, right? And then when you divide it by z, you get what? Z squared here, right? Yeah, that's actually the next scenario. So now, if you look at the root set here, you got a 1, you got a 2, you got a z squared, and that's actually a double root at z equal to what number? 0, right? Yeah. So when you do the partial fraction expansion, and you're going to have to add another one. There's a d over z squared here. Okay? Yeah. That's actually my second scenario. Yeah. And then, of course, now if you think about what happens at the end, you multiply the z back to here. So here you got the z canceled. You cancel one more z, it basically becomes just d over z. And that's a delayed direct delta function. Right? So because when you have a delayed one step, you got a z to the power negative 1. Okay? Yeah. So it's all there basically, right? If you follow the process, it's all there. You just have to look at the table to find the corresponding z table, the term, and then the corresponding inverse of z. Okay? Yeah. So that's your first case. Let's look at the second case, which is what I said when the poles are real, okay, and repeated. Okay, when poles are real and repeated. And by the way, before I move on here, I think it's we'll have to introduce that. We're going to have to look at this one too. The value of a and b at here. So this a b. There's a name for this. They are actually called residuals. Okay, yeah. So they are also called residuals here. Because in MATLAB we have a command called the residue to help us to find the values like a and b. This command called residue. I'll show you how to use that. Okay, so these are called residuals here. So number 2 case, when poles are real and then repeated. And I write down what do we mean by real and then repeated. Okay. So let's see. I'll use an example here to go over it. Okay. Okay. So here is an expression for x of z. If you look at the denominator, and apparently there is a root at z equal to 0.6, and there is also a root at z equal to 0.5, but however this is a z minus 0.5 times 2, so this same root is repeated twice. It's basically like a z minus 0.5 times z minus 0.5 and then times the next term here, right? Yeah. So this term repeated by twice. When you do the z transform as usual, we divide it by z first. Okay. So we divide it by z, and that z term, okay, on the denominator will be gone. Okay, with a numerator. So this is going to be like this now, and then we will expand partial fraction, do partial fraction expansion on this one here. So the results essentially what you get here is. Just be careful here. So you get a over z minus 0.5 squared plus b z minus 0.5. So for the same term z minus 0.5, okay, you got to repeat, not the same, but repeat twice. There's a power here, there's a first order here, and it depends on how many times it repeats, right? If it's a cubic term, then your first term is actually z minus 0.5 to the power 3. And finally, you get c over z minus 0.6. So now, in this case, you have 3 residues at here, right? 3 residues here. You can start by finding the residues b and c. So they're actually quite easy to find for b and c at here. So for a and c actually. Okay. So for c value, okay. So this one here, this is essentially more or less like the same as finding a and b in case number 1. So all you need to do is you use this z minus 0.6 multiplied by this x over z divided by z, which is this term here. Then you set the z equal to 0.6. So it'll cancel this first, and then substitute z equal to 0.6 into the rest of the term. And you can literally see that z 0.6 minus 0.5 is 0.1, and then to the power of sorry, I actually use a different number here. Yeah, so what do we get? It's a pretty big number, right? So 0.6, 0.1, 0.01, so should we get 100, isn't it, right? Yeah. Okay. And then we can do the a value a value here. So that's actually easy to do. So this one here, you do it, you use 0.5 to the power of 2, okay, so which is the denominator, and divided by z, and let the z equal to 0.5. Okay. So now this time, what do we get? Now we cancel that and plug in 0.5, negative 0.1, so negative 10. Okay? Yeah. Now the last one, which is the B one, this one you do need to remember a formula now. Okay, I'll write on this one here. Okay, so it's a little bit it needs a little bit more computation. So what you do is you can literally rewrite the expression for the a here. So you do this first. So multiply this x over z over z by z minus 0.5 to the power 2, and then what you have to do before you do the substitution, you have to do a extra step of a derivative with respect to the z. So whatever you get out of here, and you do a derivative with respect to z. Okay. So finally, you substitute z equal to 0.5 into this remaining expression. Okay. So let's be careful here. Actually, I didn't write down the results here. So let's maybe try it together. Let's see what do we get here. When we do the multiplication at here, we get basically 1 over. Okay, we do get this, right? Yeah. And we do a first order. This is basically to a derivative for this fraction at here. Okay. And what does that give us? We've got a negative 1 over z to the power 6 square, right? Yeah, the derivative of that. Substitute z equal to 0.5 into this term here. So negative 0.1, and then becomes 0.01, then become negative 100. Okay. That makes sense? Yeah. So now you got your A, B, C. So you got your A, B, C at it here, right? Yeah. the other approach is I always encourage you to hand calculate this kind of simple case manually. But as I mentioned, you have a command called residual in MATLAB to help you find this ABC value at here. Okay? So, for example, in this particular case, so what we're trying to find, basically, we're trying to find ABC based on a fraction, which is this, right? Based on a fraction of this. So you have to, what you have to do is, in MATLAB, when you enter command, you need to enter the command to form the, basically to form this numerator and denominator for the fraction first. For the numerator, apparently you'll see it's just a 1, so you can just see, okay, my numerator variable equal to 1, and then your denominator, and let's say in this case here, it's a multiplication of 3 factors, right? So this one multiplied by itself twice. So you can multiply everything out and find a coefficient to do the numerator denominator. That's fine. But you can also use this command called the convolute command. So basically, what you do is you convolute this guy here. You use 1.5, so 1 negative 0.5. So that's basically sorry, not as a negative. Yeah, it's negative, right? Yeah. So this is a z. This is negative 0.5. So z, the coefficient for the z is 1, and then negative 0.5. You multiply the term by itself. So that this convolute here give you that z minus 0.5 to the power 2. Okay. And once you get this, you do another convolute with 1 negative 0.6, and that's how you can get your denominator, right? You can get denominator here. Okay. So once you get your numerator and denominator, then you're ready to use this residual command. So you say, okay, residual, call the command, okay, and plug in the numerator and the denominator. Okay, so plug in the numerator, denominator, and then it'll return some information. And typically, you return 2 informations. Okay, you want 2 information to return. One information is, of course, the residuals, and the other information is the poles. Yes.
What type of calculator are you able to find fractions?
What type of calculator? I think in my case, regular calculator would be enough. Yeah. There are matrices involved in linear algebra, but I typically never get beyond 2 by 2 matrix, which works well enough for hand calculation, right? Yeah. There are little bit inversion, which 2 by 2 inversion. You'll have the formula, right? So I don't think the computation-wise, you need to use a sophisticated engineering graphical calculator, that kind of thing. Yeah. So is that good? See, that's the thing. I want you to show your ability to do a hand calculation of very simple matrices like 2 by 2, right? Yeah. I think last year I said no, because but actually it probably doesn't matter. But we'll see, right? So that should be your least concern. Let's put it this way, okay? Yeah. Yeah. Even if you have a really good calculator, it doesn't matter how well you're good at using the calculator to a linear. If you don't understand concept, it still doesn't help, right? Yeah. Anyway, so let's come back to this one here. Of course, computer is not going to be allowed, so you can use the MATLAB to help you in the exam. This command residual will return. So the R at here, okay, is basically the residuals. This A, B, C that we're talking about here, okay, and the P at here is the poles for the system. Okay. So the MATLAB will list all of the available poles. So for example, you may have a 0.5, 0.5, 0.6, right? So in this case, so that's going to list you the 3 poles that are here. And also we will list 3 residual values for the R, right, A, B, C. Okay. So the first one corresponding to the Z minus 0.5 to the power 2, the second one corresponding to the other one, and the third one actually be this. So that's how you will use this residual command here to help you. Okay. Yeah. So back to this question here. Let's say I got formula A, B, C now, right? So let's rewrite this a little bit here. So x of Z, okay, equal to A as we got is 100, right? No, yeah, negative 10. So negative 10 divided by this one times Z, and then plus B is negative 100. So negative sign here. And then C is 100. Okay, like this. That's your results right here. So now time to use the table now. So use the table to find the inverse Z transform. So if I look at the table here, which one has Z minus? So here you got this one here. So you got Z divided by Z minus A to the power of 2, right? So you get this one here. The only thing is this term here has what? Has an A at here, right? So you need a little bit of manipulation at here. So let me manipulate this term a little bit before we write it down. So let's see. Here is Z minus 0.5 to the power 2 and Z. So literally you should have a 0.5 Z, right? So this is your A value, right? Before you can make use of that table. But we cannot just add a 0.5, so we have to divide 0.5. So but what does that mean? That basically means there's a 10 divided by 0.5, which is 100 divided by, so there should be 20 added here, right? So instead of a 10 now, it should be 20 here. Does that make sense? Yeah. And the rest of the 2 terms, I don't think you need to, this is Z here, you need to do any modification, so you can keep it. So now I can find my x of k. The first one here, there's a negative sign, negative 20, so here is k times a to the power of k. So 20 times k times 0.5 to the power of k. And then minus this 100, z minus this, so 0.5 to the power of k. And last one is 100, 0.6 to the power of k. So that's your inverse. And the k start from 0, 1, 2, like this. Okay. Is that good? Yeah. So that's your second case. Okay. Yeah. So let's look at the third case. Okay. This one is just a bit of work at here. Okay. Needs a little bit of work, which is probably the most sophisticated case, okay, among all 3 right here. Okay. And in this case, this is basically when your poles are actually complex conjugate. Okay, so there's a complex conjugate pairs of poles exist. I'll write it down this example here. Okay, so let's see. I have x of z equal to 2z, okay, divided by z squared minus 2z plus 2z minus 0.5. So here is an x of z expression. So if you look at the poles of the system, which is denominator setting denominator to be 0, so you do have a real pole here, which is 0.5, right? Now, if you let z minus 2z squared minus 2z plus 2 equal to 0, okay? If you set this one equal to 0, and you'll find the solution for the z, okay, is 1 plus minus j. So it's complex. So it's a pair of complex conjugate poles. For the quadratic term, when you set a quadratic term to be 0, and if there's no real term, no real solution, the complex conjugate poles always appear in a pair. Basically, one always is positive and negative. Okay, so one is top, and is the bottom, right, on the complex plane. Okay. So that's what we mean for this case here. Now, to solve this kind of inverse Z transform, there are actually a few different methods here, but I'll present you the one I think that's the easiest one here. So what you do is, okay, you don't need to do any simplification here, okay, but of course you do the division first. Okay, you do this division first, and then we'll apply this partial fraction expansion on the rest of the expression here. Okay, so because you have a complex conjugate posted here for the first factor, the z squared minus 2z plus 2. So what you do is you basically have a partial fraction for this one. Now the numerator here is you use az plus b, so one order less than the denominator, so az plus b. Okay, yeah. So you'll see how we can find the inverse. Okay, once we get the answer for the a and the b. For the z minus 0.5 term, that was easy. So that's the same as the other real roots term. So just use a c over this. All right. So that's your partial fraction expansion on this kind of scenario here. Okay. Yeah. So now the question at here, the next question basically is you need to find a, b, c, right? You need to find a, b, c before we can use the z table to find the inverse z transform. So the typical way at here to find a, b, c here is what you do is you will put these two fractions, okay? Put these two fractions back into one fraction again. So you do this at here. Combine these two terms or two fractions into one fraction again. Okay, and when you put these together, basically you get so it requires you very careful writing in here to miss any terms. Okay, so write a few more steps as possible just to make sure you have everything there. Okay. Okay. So now I'm gonna the denominator. I'm not gonna do that. I'm not gonna change anything. The numerator at here. Okay. So the numerator. So what we're gonna do is we're gonna expand the numerator at here, and then combine similar terms together. Okay. Combining similar terms basically means if you look at the first one, you got az times z, right? What do you get? You get az squared. And here you also get a cz squared. So you combine these two together. That's called combining similar terms. So basically you see you get a plus c times z squared. Okay, so if you do the rest of the things here, so then here for the z term, there are a few more z terms here. There's a b times z, there is a negative 0.5 times a times z, so there's a number of terms to add together for the coefficient for the z. Okay. And finally you combine all the real terms together. So the real term here you have 0.5 times b, right? So 0.5 times b, and then plus 2 times c. That's the new numerator. Okay, this is the numerator here. And this numerator is actually not new. It's just a description of the same numerator that existed, which is here, right? This is your numerator 2, right? This is 2 here, You remember, this is what we're working on. This is our numerator. So basically, it looks scary here, right? So this whole thing here, that actually just equal to 2. Okay? Yeah. So the question basically is, what value a, b, c will make this whole term equal to 2? Right? That's the point. So you use the so-called comparing coefficient method. Okay, compare coefficient. So compare coefficient basically means, you see, the numerator, actual numerator is 2. So there is no z square, z to the power 2, or z term in this numerator here. So basically means what? This a plus c here equal to 0. And then, that's good. So then negative 0.5 times a plus b minus 2c. So there's no z coefficients, right? So it should also be 0. And finally, it's constant term. And that's the 2 you're looking for, right? That's the 2. So that's the results that by comparing the coefficients between the two numerators, okay, the available one and the one from the partial fraction expansion. 3 variables, 3 equations, and you will be able to solve for a, b, c. And a, you'll be able to solve, which end up to be negative 1.6, and b is 2.4, and c is also is positive 1.6. Okay. Yeah. Is that good? Yeah. Yeah. If you recall, actually, there should be a very similar concept for inverse Laplace Laplace transformation when your roots for the Laplace term is a pair of complex roots. Okay. Comparing coefficients. Now, you do have a shortcut for finding the value of c, okay, which probably can help you solving the 3 equations that are here. Because see, if I know what the c is, I can immediately solve for b, right? Yeah. So if you're coming back to this one here, you'll see that c is just a coefficient, the residual for z minus 0.5 term. That's the same kind of a scenario as a case 1, isn't it, right? So the calculation of c, you could be just doing this. So use the same formula, z minus 0.5 times x of z divided by z. Then you let z equal to 0.5, and now you will find the c value. Okay. Yeah. So once you find the c value, then you can use the equation, plug into the equation here, find the b and find the a, which much easier. Okay. Yeah. Okay. So we're not finished yet. This is basically maybe 2/3 of the question to solve, because we're solving for the inverse of the x of z here, right? So let me rewrite the x of z now, which is negative 0.6 times z squared. Okay, because now we're going to multiply the z back to the right side now. Okay. So multiply the z back to the right side, and we get our x of z, which is this. Okay. So now time to do inverse z transform. So inverse z transform, the second term is easy, so that's just 1.6 times 0.5 to the power of k. It's this term here, right? That's not very clear yet as to what will be the inverse of this term in here. However, if you look at the existing z table, okay, if you look at the existing z table, let's just see which one has a denominator that is a second order right here, right? So you look at this one here, so basically you got what? Here, here, or here, or here. You see that? If you look at the denominator here, so those are basically second order terms, right? That's a second order term here, okay? Yeah. And same thing for the last 2 rows that are here, right? For the last 2 rows. Okay. So which one do we use? typically you actually just have to use these two. That should be enough, okay, for finding the inverse. Okay, so these two basically is what we're going to try to use at here. All right, yeah. So basically, we're going to try to use. Okay, so if you look at, I'll just rewrite one in here. So here is x of k, and the corresponding z transform like this. So that's from the z table here. Okay, that's from the z table, and you do have the a to the power of k sine bk. Okay, right? Yeah, and you know what? Maybe I'll just write this term here too. So a to the power of k sine bk corresponding to az sine b, and then same denominator. Okay, so we're going to try to make use of this at here. Okay, yeah. Okay, so how do we make use of these existing results for the particular question at here? Okay, so let's look at this term. Okay, look at this term here. Now that term, if you look at the denominator, okay, that's exactly in the format of this, right? That's in the format here. The numerator, yes, but somehow if I wanted to use these results, it has to be consistent. It has to be exactly in this format. Basically means if this is z squared, then the second one, the coefficient of z, has to be what? A times cosine z, right? If I want to use this one here, the coefficient for z has to be a times sine b. So that's how we can make use it, right? So which basically bring us for this term here. So I'm probably let me just work on this one here, okay? I will have to manipulate this one carefully, okay, without changing it to match the format as this and that. Okay? Yeah. So that's the point here. Yeah. So how do we manipulate that? First of all, let's find out what the a square is, right? Or what the a value is based on the available this one here. So if you look at this formula, this is z squared minus 2z plus 2. This is your 2, this is your a squared. So basically your a squared equal to 2, right? So a squared equal to 2 here. And a is root 2. Okay? Technically, a can also take in which other value? Negative point root 2, right? Yeah. You can use that negative, but you actually will end up with the same results. Okay? So if you choose the equal to negative root 2, you will end up with the same results. And if you're interested, I'll show you how. Basically, it doesn't matter which number you pick. Okay? Yeah. So we'll pick the positive one equal to root 2. Once we got a equal to root 2 now, so let's look at this coefficient for the z on the denominator. So the denominator here is what? 2a cosine b equal to 2, right? So in this case, so this 2a times cosine b equal to 2. And we just solved a at here, which is root 2. So that basically brings us cosine b equal to what? 2 cancel, so 1 over root 2. Okay, so cosine b equal to 1 over root 2. And what does that mean for the b value? B is pi over 4, right? 45 degrees. Okay. All right. So now I'm pretty clear now. I need to manipulate this numerator, right? This numerator here or here to be how much? To be, this is a times yeah. This is a times sine b, and this is a times cosine b, right? So you know exactly, because you got an a here, you got cosine b here, And then sine b, of course, you probably need a sine b, and which happen to be the same as cosine b, which is 1 over root 2. Okay, yeah, that's what we're trying to manipulate into, right, for the numerator here. Come back to this term here. So now we start the manipulation now. Okay, so let me rewrite that term. I'll just rewrite the first term here. I'll just rewrite the first term. All right. First of all, you know, there's the z squared in front of z squared is nothing. It's 1, right? It's 1 here. So I will just simply take this negative 0.6, okay, out of the picture, and that gives me a z squared. Okay. So the coefficient becomes 1 now. And then, but then this one here will be different. So this will be basically 2.4 divided by 1.6, right? Yeah. If you use a calculator, 2.4 divided by 1.6 give you 1.5 here. Okay. That's how, after you take this 1.6, negative 1.6, okay, in front of this whole expression. So negative 1.6 inside this one here. Okay. So I have a z square added here. I've got a z square, so that matches this z square, right? And then what's the coefficient for the z here? It should be a times cosine b. So what's a times cosine b in this case? A times cosine b equal to, no, a times cosine b equal to, so 2 can equal to what? 1, right? 1. So I need only 1 here. See, right? So I will need a minus a z1 in order to make use of that table. So which means I have to minus another 0.5z. That make sense? Yeah. So divided by the same, okay, denominator. Okay. So and now I will basically rewrite this one into 2 terms. One term is this, and another term is this. So z squared minus z over, okay, and the other term is 0.5z negative, and divided by z squared minus 2z plus 2. Okay. So up to this stage, you can immediately find what the inverse z transform from the table based on this now, right? And the second one, this one here, I wanted to use this one because the corresponding z transform, the numerator has only a z term, right? And in this case, what does a times sine b equal to? I have a equal to root 2. I have a sine b equal to 1 over root 2. So a times sine b equal to, also equal to 1, right? It's also equal to 1. So the coefficient here is 1. So actually that's not bad. So basically you can consider the 0.5 in front of this whole thing. So this is z divided by this. You got it in the table. Okay? You got it. So overall, your x of k, right? So let's see, your x of k equal to negative 1.6 times the inverse of that, okay, the inverse of that, which is a to the power of k cosine bk. So a we already find is a root 2. So root 2 to the power of k, and then times cosine bk, cosine pi over 4 times k. Okay. We'll leave that in the bracket. And then this is 0.5, and this is sine, okay, so root 2 to the power of k and sine pi minus 4 to the power of k. And don't forget the c term, which is 1.6, 0.5 times to the power of k here. Right. That's your inverse z transform. Okay. and for k starting from 0 to infinite. Okay. Good? So there could be a combination of this case 1 to case 3, when you put things together. But if you follow the steps, right, it shouldn't be too complicated. This is already kind of combination already, right? So this is a combination already. Okay? Yeah. So if there's a question, that's probably the maximum difficulty that you probably see at it here, right? So just follow the steps carefully. I think that you'll be able to find this. Should be pretty simple. All right. That's inverse Z transform. Inverse Z transform. And before we essentially up to this stage, I think it's all review, right? Yeah. So well, actually not for mechanical, right? For mechanical students, brand new stuff. For electrical, more or less like a review based on your DSP course or some other courses. Okay. Yeah. Before we move on here, I just want to touch upon maybe a simulation concept added here. Okay. So essentially simulation using MATLAB. Okay. Now you remember, before we talk about simulation, remember last lecture I mentioned about a command called iztrans, right? Iztrans. You can always use this command actually to find the inverse Z transform. Okay, especially like this one, you can also use it. All you need to do is create a numerator and denominator, okay, based on the given x of z. Then pass the numerator denominator to this itrans. You'll find the inverse z. Okay, so you can always verify using MATLAB. So in terms of simulation, let me just use my MATLAB to quickly go over this thing. We'll come back this to detail later, okay? But at this stage, so I'll just quickly go over this idea here, how to use MATLAB to simulate. Okay, so let's see, you got you were given a this is what we later will call a pulse transfer function. So we got one of this expression given at here, okay, and we wanted to know, basically what is this g of k, with the inverse z transform essentially. Okay, now in terms of the simulation, it has to involve the idea of a system idea or input output idea here. So let's say g of z equal to n of z over d of z is given. Okay, so if you're given this, okay, I think you should always try to think of this given g of z, okay, as a system concept, which basically means the g of z, okay, in system concept. The g of z equal to your output over an input. So this is the concept. So that where does g of z come from? It comes from a ratio of this output y of z over the input x of z. It's like basically a block like this. Okay. Right. So always thinking in terms of this kind of idea here. So now, if we're going to try to simulate this g of z, it's like we're simulating this system right here, right? The system. Yeah. So what does that mean? Basically, sorry, I write it wrong. So this is x of z. This is y, right? So input, output. Okay. Input, output. Okay. So if I give an input, then I got a certain output here, right? Yeah. Now, think about this scenario here. If your x of k, your input, let's say your input is actually Kronecker delta input. And what's the corresponding x of z for Kronecker delta? We just had it's what? Equal to 1, right? Or z is equal to 1, okay? So if your input at here is Kronecker delta, your x of z equal to 1, then what is the output y of z based on this system? So that basically means your y of z equal to g of z. Okay. So if I want to find out the y of k, right? You do an inverse z transform, you get your y of k, which is basically you get what the system output looks like when your input is Kronecker delta. Okay? So essentially here you're doing inverse z transform for this guy here, right? For this guy. Okay? Yeah. Now this is a very so this one here, so that's why we call it sometimes we call it impulse response, right? Because this is impulse response that is here. Okay, I should draw the arrow here. That's the impulse response because input is delta k. Okay, and this g of z, okay, this g of z here, which is whatever is given, okay, is actually called impulse transfer function. You know, not a transfer function, but it is an impulse. You know, this is z transfer function at here. Okay, in Laplace we call it impulse. Laplace transfer function, right? For any system, when you have a transfer function given, that's impulse Laplace transfer function. Okay, yeah. So okay, so that's the point here. You try to think of this in terms of a system concept. So let's say if this is a given at here, if I want to simulate this system, I would think of a way to, okay, I'm going to give the system a Kronecker delta input, okay? And then what I get is the inverse of the g of z, or the output of system, or the impulse response of system. That make sense? Yeah. So this is at the point how we can do this information in simulation here. So this, if you look at the simulation here, I'll just show you the commands here. First, create a numerator to denominator for the g of z, right? That's given system, and then we create a Kronecker delta input. So you create an array of a signal with only the first element equal to 1, and the rest of them are all 0, right? So that's basically Kronecker delta, right? Yeah, technically it should be infinite, but only using 42 zeros after the 1. I mean, you can use more zeros after the 1. That's fine, right? Yeah, depends on system response. Then you can use the MATLAB command called filter. Okay, this one is probably in the DSP toolbox. You can use the filter command, given the numerator, denominator, and input. So that's the system concept now, right? So you have a system represented by the numerator, denominator. You have the input represented by the R, and then command filter will present you the results of the impulse response. Is that good? Right? So you will get a response basically which is y of k looking like this. Okay, so that's your y of k. Well, that's basically the simulation idea here. Okay, and you use a stamp basically that draw the little circle and with this thing here. Okay, that stamp command will draw this thing at here. Okay, yeah. So try it. You could also try another command. So basically, what I'm talking about, there's a filter command. There is also a command called IMPZ. So what does the same thing? So if you use IMPZ, this is also a simulation for impulse response at here. Okay, yeah. Now, of course, later here we're gonna not just impulse. So what if the input x of z is actually a step input, right? That could be very well the case. Okay, then you might want to simulate the step response of the system. So there's another command called step z. Okay, you can also use that to simulate this command. So just help IMPZ or step z. You'll see how to use the command. It's very straightforward. All right.
So
Yeah.
IMPZ is the impulse
Yeah. This is your step response. Yeah. Good. All right. Yeah. It's a little bit awkward here. So maybe let's just stop here. And I'll continue on the next lecture. Impulse sampling. Okay.